Welcome to the Staged Functional Programming in Spiral playlist. I, Vilo, will be your guide on the path of functional programming enlightenment. In today's video, we will explain to you what a language with staging is and how it can be used to create programs unlike in any other language that you can imagine. There are similar techniques in other languages, but they are poorly designed, and Spiral is the only language which gets to the essence of them, and in turn is a lot closer to the root of what programming truly is. Originally, when Ghostlike started work on Spiral in late 2016, he was dissatisfied with how hard it was to create a GPU-based deep learning library in F#. So he started work on a language with a stronger type system that would allow him to propagate the types more deeply. It was just an urge that he followed rather than any specific plans. F#'s type system just felt so restrictive to what was possible. He had the feeling that it should be possible to propagate a lot more information through it. At first, he studied academic papers in the literature, but they didn't strike a chord with him. So he ignored the academic work and followed his own intuition, relying on the winds of creativity to steer his sailing ship. 3 months into it, he realized that he was working on a partial evaluator. Imagine a simple expression, something like C equals A plus B. Suppose A and B are known at compile time. They could be something like 2 and 3. Then you could evaluate the expression at compile time, outputting 5. There would be no need to generate the CPU instructions in the compiled program. Just to add a few constants, you could just go to the final result. Suppose one of the variable's values turned out to be unknown at compile time. You'd only know their type at most. C equals A plus 3. C equals 2 plus B. C equals A plus B. You'd have to generate the program to evaluate those expressions at runtime. Let us give you a little demo in Spiral. That dying function you see Ghostlike typing out has the effect of pushing a compile time value to the runtime stage. If it wasn't for them being present, it would have just outputted 5 like we showed you in the previous example. This is how dyning is implemented in the core library. It is an inline function with a tilde annotation on the first argument, but otherwise it is identical to the identity function. You might be asking yourself, so what? Why is this so useful? Because you can use it to control specialization of functions. If the variables are known at the compile stage, the join point will specialize them to literals. But if they are known only at the runtime stage, the join point will factor them out into function arguments. You can get this kind of magic very easily in Spiral, without messing with template arguments like in C++ or metaprogramming systems. Join points are flexible in Spiral and can be put anywhere. Either way, they will get compiled into a method in the build output, but whether they will specialize the integers as literals in the function body or as runtime arguments depends on the information content of the variables being passed into a join point. So what, you might be asking? The ability to inline and specialize might be useful, and sure, those other languages might not have this kind of capability and don't even see the point, but where this capability really starts to shine is when it comes to inlining functions. This program is really great, and if it is your first time witnessing this, take a moment to think about it and admire it. You can't express this kind of program in F# at all. F# has let inline, and it has the inline if lambda annotation, but that would just inline the whole function. The same goes for pretty much any other language that we've looked at before starting work on Spiral. And to us, this is really important because functions are the basis of abstraction. Sure, many other languages allow the passing of functions into another as an argument, but they don't offer the kinds of guarantees that Spiral does. So in them, the best you could do is express a program such as this. In here, we are actually pushing the whole function to runtime and creating a closure as a result before passing it in. In F#, a closure is a runtime function, but in C, for example, it would be a struct with a function pointer and an environment holding its runtime variables. Think of closures as fancier versions of function pointers. We apologize for not showing you the full compiled program here, but when we compile the program on the C backend, we get 130 lines of code rather than 24 that are in the F# version. As closures are heap-allocated structures, what happens when we try to use them on the FPGA backend is that we get an error. At least that is what we thought would happen, but we forgot we left a small window of opportunity to compile them. When function closures don't have any arguments on the FPGA backend, they get compiled to straightforward function pointers. Let's extend the program so that the environment of the function ends up capturing a runtime variable. We just added a y variable and dined it so it is a runtime one. Then we extended the operations inside the lambdas so they involve y in some fashion. The three programs we've provided in the top right corner for your perusal are in fact equivalent and compile to the same program that you see below. The main difference is that we factored out the shared functionality in the lambdas. This is just a small demonstration to show that inlining in Spiral is composable. If you mark a function as in, it isn't a suggestion to the compiler that it should inline it like in most other languages. You have a rock-solid guarantee. Now, when we try to run it on the FPGA backend, we do get an error. This is not to say that functions turned closures on the FPGA backend cannot have free variables in them. Suppose we removed the dyn annotation from the y variable and leave it as a compile time constant. Then if we tried compiling the FPGA program, this is what we'd get. It is a bit long, but you'll see that the compile time literal 10 from the y variable is being added in all the closure methods as expected. We understand that these, whether a variable is a compile or a runtime one, are somewhat low-level concerns, but what is unique about Spiral is the high-level approach it takes to enable systems-level programming in a functional language. If this was C++, you'd be buried in bad syntax. And what does the C++ standard say about composing two inlineable functions? Does it give a guarantee? We think not. Spiral, in our view, is how a language designed for systems-level programming should look like. It is concerned about the right things. That is how to avoid heap allocating the abstractions, enabling its expressiveness without restricting its power. We'll say one thing. In our almost a decade of programming, it is very rare that you'd have a need for actual closures. You rarely need to put functions into arrays and heap records. Most of the time, when you are passing them as an argument to another function, you'd really prefer for them to be inlined at the call site. And Spiral does make that quite easy. A basic rule of thumb you can trust when programming in Spiral is that when the information flows forward, it gets propagated at compile time, and when it flows backwards, it gets pushed to the runtime stage. What do we mean by flowing backwards? We mean when the variables are being returned from join points from if statements whose conditional is unknown at compile time and from match statements whose cases are not known at compile time. They also get dined when they get put into arrays and layout type instances. Are we forgetting anything else? We don't think so. Those are all the situations when the dining happens automatically. Of course, how it happens explicitly via an annotation is something we've already shown. We think these rules take the guesswork out of when the inlining should happen. In order for you to understand how Spiral works, you need to be aware of how its bottom-up segment works. Take a look at how when we try to add an integer to a string in the top-down segment, we get a type error as expected. If we told the type inferencer to go away, what would happen is that we would no longer get that kind of error. It would disappear. We'd only actually realize the error when we tried compiling the program. If you copy-pasted the error into a new tab, at the bottom, you'd see what the error is. In this case, the partial evaluator is telling us that the two literals don't have the correct types. We also get a trace along with the error message. Typically, we're mostly interested in the line on which it occurs, but the fact that there is a trace is telling for how the partial evaluator works. As you could guess, it executes all the statements line by line. The reason we call it bottom-up is because it starts with the main function, which is the last function in the final module that is being compiled. This is not to say that you cannot have main functions in other modules, but the modules do have to obey linear ordering, so any other functions beyond the one being compiled wouldn't be accessible from the main function, defeating the point of it. Anyway, so the partial evaluator starts from main and works its way forward, evaluating what it can at compile time and pushing the rest to runtime. Every time it encounters a join point, it does a match on the free variables in the environment, and if it doesn't find the same configuration in the dictionary, then it evaluates it. At the end, it stores the compiled result for later use, in essence, memoizing the join point. The next time it stumbles upon the same join point, it just inserts a link to it, saving on the compilation time. Partial evaluation is pretty powerful. Whereas the top-down segment has a type system limited to first-order logic, the bottom-up segment is much freer. Since it is always dealing with the actual variables, the partial evaluator always knows the type and the exact value for the compile time variables. Therefore, in the bottom-up segment, you can do things that would be absolutely impossible in the top-down segment. The reason we are opening the real core module is because the functions there don't have Foralls, and not having to pass types into them makes them easier to use in the real segment. In the top-down segment, the type inferencer applies the Foralls automatically for us, and we can't even apply them manually there, in fact. As you can see in this example, in its true segment, Spiral will evaluate the conditional of the if statement, and if it is known at compile time, it will only evaluate one of the branches. In the real segment, the match statements are a lot more flexible. Whereas in the top-down segment, the types of the structures being matched on have to be the same in every union case, that isn't the situation in the real segment. You can mix tuples, records, literals of different types, and anything you want in the real segment without issue. None of this has any kind of runtime cost. Let us just wait for a few moments for Ghostlike to finish writing it out. And as you can see, when we are pattern matching on the shapes of compile time known structures, like tuples in this case, and records and nominals, we don't have to worry about branch returns. Here is an example of pattern matching on types directly. This is one place where the behavior of the top-down segment and the bottom-up differ. In the top-down segment, the type annotations are removed before the partial evaluation phase, but in the real segment, they are left in. You can match on any kind of type using this, and as you've guessed it, it has no runtime cost. In addition to the regular match statement, just in the real segment, there is also a typecase statement. Spiral has two different scopes, namely the type scope and the term scope. It has two different sets of environment it uses for them under the hood, and the type scope can only hold types. Since Typecase only matches on types, what we are doing here is getting the type of the X variable using the grave operator. Then we match on it using the Typecase. And you can see the compilation output in one of the images. For this slide, we also demonstrate the use of one of the inbuilt operations, which is print static. When the partial evaluator encounters that one, it prints out the type or the term to the console, that being F64, the 64-bit floating point number. As we said, Spiral has types and terms in different environments to keep them segregated. This is a deliberate design decision. In the 2018 version of Spiral, they were in the same environment, and as a consequence had issues with spilling when closures were unintentionally returned from join points, causing a huge mess. Now things are much better. What happens when you try to apply a for-all with a term is that you get an error, and this is a lot better than accidentally applying to a wrong variable. The way to apply functions with for-alls is to first supply the type and then the argument. Since this is the identity function, we can just use the grave operator once to enter the type scope, and then use the grave operator again to enter the term scope. Then we can pass the X into the type scope, which will strip away its term information. Then we can pass its type into the identity function. The subject of doing type inference in the real segment by running term-level programs is sophisticated. And quite frankly, in the version of Spiral that you see here, we did everything we could to get away from it. Whenever you can, try to rely on the top-down segment, and you won't need to concern yourself with these aspects of the language. Let's do some actual programming now. What you see on the screen here is the type of the fold and the left-to-right fold function. It is pretty usual stuff for functional programming aficionados. Let's try to optimize it in Spiral. If you look at the output, you'll see that there are closures being allocated, so let's try to get rid of those. The let statement in Spiral is equivalent to writing out this expression with an inl. The let statement is just a bit of syntax sugar over the INL that puts the dyne annotations on all the function arguments as well as a join point around the body. In order to get rid of the closures, all we need to do is to allow the fold function to specialize the function being passed in as an argument into the join point. By removing the dyne annotation, we can keep it as a compile time variable. This is passable, but we can go a lot further. Consider that both the list and the state variables are statically known at compile time here. If the head of the list happens to be statically known, then we don't need to put a join before evaluating the function. What we can do is test whether it is a runtime variable using the var_is function, which always returns a literal true or false. The partial evaluator always knows whether a variable is a runtime variable, or known at compile time. If it is a runtime union variable, then it pushes the state to runtime and runs the loop body as usual. If it is statically known, then it doesn't pass it through a join point and just inlines the iteration. Since in the compiled output the lists are never allocated, we could even use them in the FPGA backend despite them being heap-allocated types. And since the fold function is written out like this, it will evaluate the statically known part of the list at compile time, while switching to generating the code for the runtime parts. As long as you use let statements for everything, programming in Spiral is as safe and easy as it is in any other language. You don't have to think about the compile and runtime stages unless you want to. Not only are the types the same between the two stages, the execution of the program is functionally equivalent between the optimized and unoptimized versions. The main thing that Spiral allows you to do is make the trade-off between heap-allocated memory and code size in the final output. If you get it wrong by forgetting to put a join point, here's what can happen. You get a stack overflow and the compiler crashes. If you try building a program and the compiler suddenly craps out with an exception, the most likely scenario is that you wrote an infinite loop at compile time and it crashed. Take a look at the terminal to see what is going on there. It could be a compiler error. If it is, open an issue on the Spiral repo with a minimal example. If it isn't, you'll have to add some print static statements in order to figure out what is going on. Our suggestion, if you are intending to get serious about Spiral, is to take a look at the core library. It isn't long, and it will give you a lot of insight about what the language is capable of. Let us say that Spiral is not intended to be a baby programmer's first language, but a power tool. And slowly, we will start showing you that power. Other languages are afraid to take risks, but Spiral isn't. It looks at the halting problem and challenges it head-on. Let's end the video here for now. This should be good enough to get you started with Spiral. If you found it interesting, like and subscribe. If you want to check out Spiral yourself, just install the Spiral extension on the VS Code Marketplace. That is all it takes for you to start playing with it. Also, check out the documentation on the GitHub repo main site. The link is in the description below. To the language, we recently added some new features like type-level literals, which we will be using in our next video. We hope that with these 2 videos, Spiral will feel less complicated than it was before. As much we'd like to continue, we are bored to death, and we want to get started with some serious programming. In our next video, we'll turn on our screencasting software and go into a time-lapse until the hand ranker is done. That will be a good warm-up project for us. We are really curious how long it will take the Xilinx compiler to compile the program at the end. If it is something like days, we are not sure whether the FPGA attempt will be tenable, but if it's an order or 2 magnitudes less, we might be able to accomplish our goals in this series. We are afraid of what the future holds, but we have no choice but to put our faith in ourselves and courageously move forward. See you in the next video.